Alright, in this third video, we're going to take a look at a couple of trig ideas again. First of all, we're going to look at the unit circle and identifying a point on the unit circle. And also look at some trig identities and how to simplify some expressions using those trig identities. So let's start with the unit circle. And if you remember, the unit circle is a circle that's centered at the origin with a radius of 1. So these points are at +1, these ones are at -1. The equation then of the circle is going to be x squared plus y squared. That would give its center at 0, 0. And since its radius is 1, it's going to equal 1 squared. Now we have this nice little theorem about angles and unit circles. It starts off with a position angle that intersects the unit circle. So we've got this angle alpha, rotated this way, and it intersects the unit circle at this point P. Now P has an x coordinate and a y coordinate. And those values come from starting at the origin and going over and up to get there. Now I hope this looks like a right triangle to you, where the base has a length of x and the height has a length of y, and we know that the hypotenuse has a length of 1. And when we think about our basic trig functions, like sine and cosine, well, sine is opposite over hypotenuse, so y over 1, which means the sine is the y coordinate, and cosine is adjacent over hypotenuse, or x over 1. So it will be the x coordinate of our point, which tells us that point P has an x coordinate that's cosine and a y coordinate that's sine. So what the theorem is telling us is that if we start with an angle in standard position, it's going to intersect the unit circle at the point cosine sine. So let's say we have this point A that is the intersection of the unit circle and the position angle of pi over 3. Where is that point? Like, what are the coordinates? Now remember, every point on the unit circle is going to have an x coordinate, that's the cosine. So we'll have cosine of pi over 3. And the y coordinate is going to be the sine, so sine pi over 3. Now, we know that cosine of pi over 3 is 1/2, and sine of pi over 3 is √3 over 2. So that is our ordered pair. And what if we have this other point B that's determined by the position angle 5 pi over 4? Well, we know that B is going to have to be cosine sine, so cosine 5 pi over 4 and sine of 5 pi over 4. Now these are both pi over 4 angles, so that means that the sine and the cosine are both the same, and they're both √2 over 2. Okay. However, we do have to determine whether those values are positive or negative. So thinking about which quadrant B is in, since B is in the third quadrant, that means its x coordinate has to be negative and its y coordinate has to be negative, because we go back and down. So the coordinates of our point B is not just √2 over 2 and √2 over 2, but negative √2 over 2 and negative √2 over 2. But what if we're dealing with a circle that is not a unit circle? So its radius is something else. It's not 1, not 0, or anything negative either. Well, this point has an x and a y coordinate as well. And that's determined by going over and up to get there. So the base is the x coordinate and the height is the y coordinate. It's just this time the hypotenuse has some other radius. And when we're thinking about our basic trig functions, sine and cosine, let's start with sine. So sine of alpha is going to be opposite over hypotenuse. Now if I want to get that y alone, I multiply both sides by r, and y will equal r times the sine of alpha. Similarly, for cosine, cosine of alpha is going to be adjacent over hypotenuse, and to get x alone, multiply both sides by r, and we get r times cosine of theta. What that means for us then is that for any point Q that's on any circle, the x-coordinate is going to be the radius times cosine, and the y-coordinate is going to be the radius times sine. And that also works for a unit circle if we look back, because then the radius is just 1. So what if I'm kind of working backwards? What if I know where the point is? I know that A is -4, -7. Can we find this angle theta? And more importantly, can we find sine, cosine, tangent of that angle? Maybe even without knowing what the angle is. And of course we can. We're going to do it by thinking about triangles. Because to get to that -4, -7, we go back 4 and down 7. So we make this right triangle, where this side has a length of -4 and this one of -7. Now we can use Pythagorean theorem to help us with that radius. That we know -4 squared plus -7 squared has to be whatever the hypotenuse, that radius, is squared. So a little calculating tells us 16 plus 49 is 65. So when we square root r squared, our radius is going to be square root of 65. So now we have this length, square root of 65. And the thing about trig is that trig is always easier when you're looking at a right triangle. So once we have that triangle, we can think about the sine, cosine, and tangent of theta. So theta actually goes from the positive x-axis all the way around. However, its reference angle is right here. So the sine, cosine, and tangent of its reference angle is going to be the same as the sine, cosine, and tangent of theta itself. So we could just look at that reference angle as our point of reference. And think about sine. Sine is opposite over hypotenuse. Now, the side opposite that central reference angle is -7. And the hypotenuse is square root of 65. If you wanted to rationalize the denominator, of course, we end up with -7 root 65 over 65. Also for cosine then, that's going to be the x-coordinate over the radius. So rationalize that denominator. And then we also want to be able to find the tangent. And of course, tangent is sine over cosine. So we'll have this -7 over root 65 over -4 over square root 65. If I go back to those first fractions. And there's a little bit of canceling that can happen. The square root of 65's cancel, and negative over negative is going to be positive. So this entire fraction will simplify to 7/4. Now, I've been using a handful of identities that I expect you to know. Specifically, there's 3 types of identities that I want you to know, the basic ones. And we oftentimes think about this as SOHCAHTOA. Right? So what I mean by the basic identity for sine, cosine, and tangent is that if we have this angle, theta, we can find the sine and the cosine and the tangent of theta by looking at the ratio of sides. And we think of the side opposite the angle as the opposite side, the base of this triangle, that leg that's next to the angle, as the adjacent side. And then, of course, the longest side of a triangle is the hypotenuse. Then sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. I don't necessarily know that those are identities more so than they are definitions, but one identity that we have used is involving this tangent. And the tangent, because it's opposite over adjacent, that's the same as sine over cosine. Okay? And this identity does become very helpful. Now, when we're talking about the reciprocal identities, those are specifically talking about secant cosecant, and cotangent. And all three of these are reciprocals of our basic trig functions. Now, obviously, cotangent is going to be related to the tangent, so that means cotangent is the reciprocal of tangent. But with the other two, secant and cosecant, pay attention to which one is related to which. Cosecant is actually the reciprocal of sine. And secant would then be the reciprocal of cosine. How I remember it is that when I'm thinking about each pair gets one co. So I mean, like, cotangent has its co on the cotangent. Cosecant already has its co. That's why it's paired with sine. Secant doesn't have a co, and that's why it's paired with cosine. But whatever you can do to help you remember how they're paired up, use that. And then we have the Pythagorean identities. And the Pythagorean identities comes from, basically from that definition of the unit circle. Remember, we started with x squared plus y squared equals 1. That's the definition of the unit circle. And we said that for any point on that unit circle, the x-coordinate is the cosine. So we'll have cosine squared of whatever the angle is. And the y-coordinate is sine. So sine squared, whatever the angle is equal to 1. Oftentimes we rewrite this in terms of sine coming first. So sine squared of an angle plus cosine squared of the same angle is equal to 1. Now, we can also combine this with our reciprocal identities to come up with a couple more. For instance, we can take each side and divide it by cosine squared, which would, in essence, take each term and divide it by cosine squared. What that does for us is that we'll have sine squared divided by cosine squared. Sine divided by cosine was tangent, so we have tangent squared. Cosine divided by cosine is 1, and the reciprocal of cosine is secant. So we'll have secant squared over here. Or we can go back, and instead of dividing by cosine, maybe we divide by sine instead, the sine squared. And when everything simplifies, sine squared divided by sine squared is 1. Cosine over sine, that's the reciprocal of sine over cosine, so the reciprocal of tangent is cotangent squared. And now the reciprocal of sine is cosecant squared. So we really have 3 different Pythagorean identities, with the basic one being sine squared plus cosine squared equals 1. Knowing those identities are going to allow us to simplify or evaluate some fairly complicated looking expressions involving trigonometry. For instance, here when I have sine squared of 3 pi over 10 plus cosine squared of 3 pi over 10, since both of those angles are the same and I got sine squared plus cosine squared, this complicated looking thing just equals 1 because of the Pythagorean identity. But maybe we don't have sine squared plus cosine squared. Instead, we got sine squared of x times cosecant squared of x times cotangent of x. What should we be doing? All right, well, a good kind of plan of attack for these types of problems where you have to simplify a trig expression is to turn everything into sines and cosines. So I'm going to start with that sine squared and just leave it. But cosecant, that's the reciprocal of sine. So 1 over sine squared of x. And cotangent, well, I already see stuff canceling, so I'm actually just going to leave that one alone. Because can't you see that the sine squared and 1 over sine squared, they're going to cancel and just leave us with cotangent? So that whole thing just simplifies to cotangent of x. One last example, what if I have sine squared times cosecant squared minus cotangent squared? And you're really hopeful that, oh man, I got everything squared, but you look in the middle and that's a minus and not a plus. So Man, it's probably not one of those Pythagorean identities. So let's start by turning everything into sines and cosines. My sine squared is going to stay right here. Cosecant is the reciprocal of sine. And cotangent is reciprocal of tangent. Since tangent was sine over cosine, cotangent is going to be cosine over sine. Since I'm subtracting two fractions and I have a common denominator, I can just write this as a single fraction, 1 minus cosine squared all over sine squared. And then we get a little canceling to happen. We're multiplying by sine squared and dividing by sine squared, so we have that 1 minus cosine squared. And at first glance, you maybe think, well, I'm done. I don't have another identity. But I do want you to be able to recognize this one, that it comes from that basic Pythagorean identity. Remember, the basic Pythagorean identity was sine squared plus cosine squared is equal to 1. And what we have is 1 minus cosine squared. So if I were to subtract cosine squared from both sides, we end up with this statement. So 1 minus cosine squared is equal to sine squared. So we can simplify this a little bit more into just sine squared.